Look, the exam will cover from chapter 7, the second part, beginning with atmospheric phenomena. If you're following along on this page, that would be, I think 7b here. Yeah, this chapter 7b and on. So 7b, 8, and 9. But in your book, this section begins with atmospheric phenomena. So in summary, this is what you're going to see. We'll just sort of step through and I'll summarize. And then if you have questions, we can work through some of those in just a bit. So, atmospheric refraction and mirages, just know what they are and what causes them. And then we'll get into lenses. Now the lens section will be a lot like what we saw in the mirrors. So with lenses, you need to be able to identify the lenses. Identify them too as either converging or diverging. That is, the concave lens is a diverging, much like the convex mirror. The convex lens, which is like the lens in your eye, is a converging lens. Did I say concave was diverging? Yes. Yes, so it's diverging. So be able to identify them. If I give you a picture, be able to identify them by their geometry too. Remember that concave has a negative focal length, convex has a positive focal length, and then you're going to see the lens equation. In much the same way, I think it's probably a little easier than what you saw last test with the mirrors, but you'll see the lens equation. That's this 1 over f equals 1 over q plus 1 over p. Doing that business where I give you a scenario with a lens, I may or may not tell you what type of lens it is. Okay, you'll have to determine that from the type of images that are being formed or how I describe the image. And you have to figure out things like the focal length or the image distance or maybe even the object distance. So you'll see the lens equation there for a single lens. You're going to see it for a two-lens system too, but I'll come back to that. You'll need to be able to calculate the magnification. And remember, magnification we can find in two ways. The magnification is negative q over p, image over object distance, but then it's also the height of the image over the height of the object. Now you'll need to know the types of images that are formed by all the types of lenses. Let me just go ahead and write that down here. So for a convex lens, this is a lot like a concave mirror. It's almost identical to the concave mirror because it's a converging device. You can have three scenarios: inside, at, or outside, at, and inside the focal length. These are all objects, and then I'll do the images in red. This is a real inverted image. This does no image at all. And this one is a virtual upright. Virtual images are always upright. Bigger image. All right, so the image here is going to look like this. So these are images here and here. Notice this is different from the mirrors because the virtual images are on the same side as the object. The real images are on the opposite side of the object. That's how lenses work. It's sort of different because we're refracting, not reflecting light. All right, and then with the concave lens, you have a lens that looks like this. It doesn't matter if you're in or outside the focal point. If this is my image, or excuse me, if this is my object, my image looks like this. It is a virtual upright smaller image. It's just like the convex mirror, the security mirrors. This looks identical to what we had for mirrors, except we were dealing with concave mirrors and convex mirrors. All right? You need to know those types of images. They'll help you in these lens equation problems that you're dealing with because you can determine what type of lens you're dealing with. It's probably not going to tell you what type of lens, based on the type of image that's being formed. And then it might also just ask you what type of image does this lens form in this scenario. You need to be able to describe that. All right. You're also going to see a two-lens system. I know that we did virtual objects in the lab. There'll be no virtual objects here with your two-lens system. It'll be like the ones that we did in class. If you don't know what I'm talking about, no, you should know what I'm talking about. The virtual objects occur when the object is on the opposite side of the second lens. And we're not going to see that. That's where your object distance is negative. If you don't know what I'm talking about, don't sweat it. Just look at the examples that we did in class, because those were ones like you'll see on the test. And there is definitely a two-lens system on there. All right, you're going to have to draw ray diagrams. Or you're not going to have to draw a ray diagram, but there is there is a lens, and I give you some examples of rays, and you have to pick out the correct or the incorrect rays. So there's a ray diagram, just one, but you know, it's a few points. There are 28 questions on the exam. Aberrations, spherical and chromatic aberrations. Know what they are, what causes them, and how to get rid of them. The spherical, this is due to different parts of the lens focusing light at different points. So like we did this in lab where you look at light going through the outer edge of the lens and then look at light going through the inner part of the lens, and they focus at different points. The way you get rid of that is you use an aperture, much like in your eye or much like in a camera, and it just blocks the light rays going on the outer parts of those lenses. For chromatic aberration, it's light of different colors going through the same part of the lens will focus at different points, because if you look at the index of refraction with regards to wavelength, it changes. And so if your index of refraction changes, then the light of different colors will bend different amounts. I think that's it for that chapter, yeah. Then chapter 8. We have interference. You need to be able to identify constructive and destructive interference. All right, remember constructive looks like this, where when I add them up, it gives me double the amplitude, or it gives me the sum of the amplitudes. And then destructive is when they're offset by a half wavelength. Know that those offsets by a half wavelength gives you destructive interference. And be able to identify that. We did that a couple of times in class where I gave you a question that said these two waves are offset by this amount, or these two waves travel through space and one of them travels a little bit extra distance. What type of interference do I get? Well, if it travels by an extra wavelength, I get complete constructive interference. If it's offset by a half wavelength, I get complete destructive interference. And if it's something in between, then I get, something in between, neither constructive nor destructive. This was like the mountain problem. We had some problems actually with, it's like pixie stick day right there. Sorry, what was I saying? The mountain problem, or we saw it with the speakers as well in chapter 9. So know how to do those interference problems. Know too the angles that if I'm offset by one wavelength, then that's like 360 degrees or 0 degrees. If I'm offset by a half wavelength, that's offset by 180 degrees. And if I'm offset by a quarter wavelength, that's 90 degrees. Mostly we're concerned with these. There's no quarter wavelength business on here. But either the 0 degrees or 180 degrees offset. The first is constructive, the second is destructive. Be able to do those things where I give you waveforms like we did in class, give you two waveforms, and I add them up, and you have to pick out the waveform. We had that both in chapter 8 and in chapter 9. There were a couple examples we did in class. And then we get into our double slit, single slit, and diffraction gratings. So a couple of different classes of problems that you'll see with that. You'll see calculations regarding them, and then you'll also see some relational type problems and how we get these fringes. So let's just sort of step through those. Look, I'll just put them all sort of right next to one another because they're similar but a little bit different. Double slit, single slit, and then the diffraction grating. By the way, I sent out an email yesterday on Moodle. I changed the equation sheet a little bit just to make it more in line with what we were doing in class. It was a little outdated. So, looking at these, my double slit is governed by this equation. That is that d sine theta equals m lambda, and that is for m equals 0, 1, 2, until I end. Remember that my fringes stop for theta bigger than 90 degrees. So if I ask you, and we did this in class, but if I ask you how many fringes are there, or what's the maximum order number, you would consider the angle to be 90 degrees. Because if I think about my double slit experiment, my interference pattern looks like this. My angle is from here, say, to here. This is my angle. If that angle reaches 90 degrees, then the light is no longer going to reach the screen. So if I ask you a question about how many bright spots are they, or what's the maximum order number, you would just put in theta equal to 90. And then whatever value you get, you would take the lower number. You'd round it down. We did that in class, and I think it's in the homework as well. Couple of things you need to know how to find. You need to be able to find y. And this is something I changed on the equation sheet. That y is equal to L tan theta. The expression I had before, which is in your book, was different in that it was making a small angle approximation. And so your tan theta was just equal to theta. And that's okay most of the time, but sometimes that's not appropriate. So just to make it simpler, I just replaced it with this. Need to be able to calculate for y, calculate for theta. Don't forget your order numbers here are a little bit different. This is m equals 0. This is m equal 1. This is m equal 2. We have an expression on the equation sheet for the dark spots too, where we have that m plus 1/2. You're not going to see that on the exam. I'll just ask you about the bright fringes, not the dark fringes, the dark spots. You might also see some questions like we did in the concept test where it asks, if you change this value, how does it change this value? So for example, if I increase the slit separation, d, how does it affect the separation of the fringes on the screen? Well, if I increase d, theta has to decrease. If I increase d, this has to decrease, which makes the fringes go closer together. I'm sorry, can you repeat your question? Oh, the y. Yeah, that's the letter y. Okay. I'm sorry, what now? Yes, I'm sorry, it's just poorly drawn. I was just drawing it quickly. All right, so now let's look at the single slit. Y'all okay with double slit? No, it's fast, but we can come back to it if we need to. All right, single slit is very, very similar, except a little bit different. We have a sine theta equals m lambda, but this refers to dark fringes. On the equation sheet, I think theta has dark on it, so that should help you remember that that's for the dark fringes. And so the other difference is that I'm measuring the slit width, not the distance between narrow slits. So this is a much wider slit. Goodness bless you. Goodness bless you. Here we're looking at dark spots. So this is m equal 1. This is m equal 2. Notice that that's different from the first one. Here I'm looking at dark fringes. Here I'm looking at bright fringes. The equation sheet will help you remember that, I think, because it has that dark on it. So if I want to know, say, the angle to the second order fringe, the second order dark fringe, then it would be that angle. Still know how to measure or how to calculate y. And again, that would be y to the dark fringe. I wouldn't ask you anything about the bright fringes for this. So you can imagine as you defined it, right, it would just be m plus 1/2, because you just had your light traveling an extra half wavelength in distance. But you don't see that on the test. So very similar to double slit. In fact, it looks a lot the same. If you were to look at them on the screen, they would look a lot the same in the fact that they have a very central bright fringe followed by fringes, dark and bright fringes that go on for a certain distance. Diffraction gradient is exactly the same as the double slit except for finding the slit separation. And you'll have to do this, you'll probably have a separate problem where you just have to, I give you the number of slits per centimeter and you have to find the slit separation. So remember, we really want to know this distance, the distance between slits, but I give you the number of lines per centimeter. For example, 1,000 lines per centimeter. And to find D, I just take the inverse of that. So that's 1 over 1,000, that would be 0.001 centimeters. And then probably you're going to have to, well, if you're working a problem, you'll have to convert that to meters. So be careful with that. Make sure that you do convert it to meters. 0.00, I just add in 2 zeros there, meters. Okay? You will have to do that. Make sure that you're careful with that when you see these problems, because I'm not going to give this to you in lines per meter. That's just not normal to do it that way. Okay? Am I good with this? Make sure you keep these separate in your mind. You're going to see, I think you see all three. I'm pretty sure you do in various forms. All right, let's see. I think that might be the end. Yeah, there's no Fresnel diffraction. The thing with the circular diffraction, don't worry about that. Now, with the sound, speech, and hearing, you're going to see properties of the wave. Yeah, it's chapter 9. So you need to know how to know the difference between wavelength, frequency, period, wave velocity, and how those are all affected by one another. We know that V is equal to lambda times the frequency. We saw that a bunch in our concept test. But remember that the speed of the wave is dependent only on the medium. That if I change my wavelength, the speed doesn't change, but my frequency changes. With the caveat that we saw that with a string, that's okay. Is it going to keep going? No. Okay, good. The speed is dependent upon the medium. The speed is dependent upon the medium. So if I change my wavelength, my frequency changes, not my wavelength, but not my velocity. Remember, there are different types of waves. Transverse versus longitudinal. You know, it's like the up and down versus the back and forth waves. Well, don't forget amplitude here as well. That came up in a couple of questions that we're dealing with. Now, the vibrating string. We got the frequency for this. This is at 1 over 2L square root of T over mu. Remember what these quantities are. You will have to calculate the frequency of a vibrating string, I'm pretty sure, or at the very least you'll have to, if I change a quantity in this, tell me how the frequency changes. So for example, if I double my tension, I'm going to get a √2 increase in my frequency, so a factor of 1.4. If I double my mass density, I get a lowering of frequency by a factor of 1 over √2, for example. We saw some problems like that in the class. All right, there. Speed of sound. We talked about here the elasticity of media. You know, sound travels faster in a liquid or a solid than it does in a gas because those materials are more elastic. They have a bigger restoring force that puts the molecules back into place. The production of sound. This was sort of just getting into the idea that you have multiple frequencies added up in sound waves. Multiple versus single frequencies. right? A single frequency would look like this. A multiple frequency would have a much more complicated waveform. If you've ever used anything like Audacity or any of those things where you actually see the waveform of the sound wave, you know that those are very complicated waveforms. All right, intensity. So you'll certainly see some intensity and intensity levels. That's the power over area squared, and then that's also the decibels. May I go down from here? Okay, so intensity. This is the idea that we measure the intensity as the power over the area. And remember the area, this is on your equation sheet, but we're generally dealing with spherically symmetric things, and the area of a sphere is 4 pi r squared. It's on your equation sheet, it's sort of up in the top left-hand corner. So my area has this inverse, or is this dependent upon the radius squared. And then we also dealt with the intensity level. A couple things you need to know. One is that an increase of plus 10 decibels gives you a time 10 in the intensity, right? And we said plus 20 decibels gives you a times what? 100 intensity, and on and on. Plus 30 decibels is 1,000. It's a logarithmic scale. I also want you to be able to compare two different sounds. I gave you all this expression, and we used it the other day, is that I1 over I2, if I'm comparing two different sounds, is equal to 10 times delta L over 10. We worked through a problem last time and then in class prior to that, comparing two sounds. So if I give you, say, a decibel level that's different for two sounds, and I give you one of the sounds, the intensity, be able to tell me the intensity of the other sound. Okay? Y'all okay with this? Do this. Make sure you practice. Both of these things are. Decibels are sometimes difficult for students, but if you can do these things, you should be good to go. No Doppler effect. And interference. Y'all hear me? No Doppler. Okay, interference and resonance. You will see some of this with the tubes. I know it seemed kind of complicated when we were doing the tubes, but I think if you understand the idea of nodes and antinodes, that you're probably going to be okay. And remember, with a closed open tube, I have a node at this end, and I have an antinode at this end. So this is an antinode. Make sure that you know what these things are, and that you can identify them. A node and an antinode. And also know that this, which is a distance L, is also a quarter wavelength. Right? We can look at the waveform that this is only a quarter wavelength because, well, this is a full wavelength, and I can break this down into fours. I have 1, 2, 3. This is a quarter wavelength right here. That's different for a closed tube or for a vibrating string. Remember, closed tubes and vibrating strings are the same. This is a closed tube. The wave looks like that. This has a distance that is equal to a half wavelength. You should be able to find the frequencies for those tubes, and I give you the equations for them for the open closed and then the closed tubes on the equation sheet. But I want you to be able to take this and figure out, for example, what is the wavelength of this frequency, this resonant frequency. Based on, if I were to give you the length of the tube, then you could find what is the wavelength. Are y'all clear on how to do that? Let me show you for example. So say, for example, we're dealing with this open closed tube, and I tell you that this length is 1 meter, then you know that the wavelength has to be 4 meters. I know that because I would say, well, 1 meter is equal to a quarter wavelength, and I have a quarter wavelength in the first frequency, like I draw right here, and so I solve that for lambda, and so lambda, the wavelength of that wave is going to be 4 meters. That's what I mean by that, by being able to look at those open closed or closed tubes and determine things like the wavelength. Here, by the way, if this one was 1 meter, what would the wavelength be? it would be 2 meters, right? Because that would be a half a wavelength is 1 meter, so the wavelength would be 2 meters. I just really want to introduce y'all to those resonances, so I'm not too terribly concerned with a lot of the details, but I want you to sort of understand how these things work physically. Reminder, same for string. Because a string also has nodes on either end. That's where the string is fixed on each end. Okay, so far the human stuff, just sort of basic information, I'll ask you questions. Like, for example, you know, what is ultrasonic versus infrasonic? Ultrasonic is above the audible spectrum. Infrasonic is below the audible spectrum. Know how the vocal cords, the diaphragm, the lung, the trachea, and the larynx, the roles that those play in the role in human speech production. Have any of you had anatomy? Y'all haven't. Okay. Well, it's going to be what we went over in class, nothing more than that. But just know those basic parts of the speech production. And then likewise with the hearing, know the parts of the ear, the external, middle, inner ear, what purpose they serve. I'm going to give you a picture of the ear, and I'll pick out a couple of things, and I'll ask you to identify them. All right, so know the auricle, this part, know the ear canal, know the tympanic membrane or the eardrum, know the ossicles. You don't have to know the names of the 3 ossicles, the malleus, incus, and stapes, but make sure that you know what the ossicles do. Right, they're levers. They transfer that force to the cochlea, and then the cochlea converts those vibrations to an electrical signal. But you go back over that. There's 3 or 4 questions about the ear. I want you to get all those right. It's just, make note cards, whatever it is that you have to do to memorize that. And then the vestibule and semicircular canals, remember, have to do with balance. Y'all do the up down busy thing? Nobody did it. No, you can't do it in here, man. Because you would fall on the floor, and you would bust your head open. Y'all go outside, we don't. Really? Don't do it inside.
Well, I was like, I'm going to
Right. Okay. So that's sort of a summary. Are there particular parts that you're concerned about that you want to look at? Tyler? Yeah. What page you on, Tyler? No. Because you have to solve the system of equations on that, right? Yeah. No, listen, the lens problems are considerably easier than even the mirror problems that you had on the test last time. Yeah. They'll be a little more straightforward than even the ones you saw about mirrors last time. All right. 8. Yes, absolutely. Yes, you will have a 2-lens system. We did a couple in class, but yeah, number 8 is a good one. For this one, it can have a virtual image, but not a virtual object. Because I think, let's see, it's 15 centimeters and the object is 30, so 1 over 15, 1 over 30. Yeah, that's okay. I get the final image is virtual, but the object is not virtual. You know what I'm saying? This one doesn't have a virtual object because if I have my 2 lenses like this, here's my object, my first object, my first image is over here. So this still has a positive p-value. All right, what I meant is that you will not have virtual objects. The virtual object will be with this image is actually over here. We had that in lab, but you're not going to see it on the lens. But you will see a 2-lens system. There is 1 2-lens system. Those are good questions. What else? Yeah. Okay. That's a mirror. On chapter 8, okay. What page is it on? One what? 99. What's that, Brittany? No mirrors, right. No mirrors at all. Okay, yeah, this is a good one. So here, you will see a single slit. What you want to know for this problem is what is this length? What is this distance? And so if I think about my angles, I'm going to call this y, and so that's this distance. This distance will be twice that. So I'm looking for y, the distance to the first minimum, which is what we find for single slits, right? We don't look at the bright spots, we look at the dark spots. And then I'm just going to double that. So this is my angle theta. I would say A sine theta. Sorry, that should be lowercase. Equals m lambda. And my m, my order number, is my first order. So it's going to be A 0.3 times 10 to the minus 3. Know your metric prefixes, by the way. Milli, centi, micro especially, nano. I think all of those come up on the test. I think y'all have that by now. But sine of theta equals 1 times 632.8. And then I find that angle theta. Does anybody know off the top of their head what that is? Have you found it already? Okay, well, I'm going to skip that right now just for the sake of time and just sort of do it algebraically or you know, with just the variables. So once I find theta, I want to find y. And y is equal to L tan theta. L is the distance to the screen, that's 1 meter, times the tangent of the angle theta. And then that's going to give me the value for y. And then for this particular problem, I just double it. And so 2y is the answer. You certainly will, I'm not saying you have one like this where you have to find the width of the central fringe, but you certainly will have one where you have to find the distance to particular fringes on the screen. We've done that, and this is a similar question, it's just slightly different, because you're finding the width of this one where you're just doubling that value for y. All right, what else? I feel okay about the test? Other tests on Monday? What do you have now? Wow, don't worry a little bit about it. Huh? Organics. Oh, okay.
You all get together.
Dr. T. That's all right, that's all right. Don't say that. Okay. You would multiply like 2, right? All right. Is that helpful for y'all to go through this? I'll be around this afternoon. I'm going to meeting at 2, but if you have questions, I'll be around. And then Monday morning, 2 o'clock.
There was something you said about that, and then somewhere around here, you said that something happened.
I don't remember. I think I wrote that.
I'm sorry.
That's okay. I think we can go. I'll just tell Olivia all the answers after y'all leave. I don't remember, Olivia. I'm sorry. I don't have anything written here. All right. Y'all have a great day, okay?